Greetings again. This is the Pencrest High School AP Physics 1 video series. This is video 6F, collisions in two dimensions. Now what we're going to do is apply conservation of momentum to collisions in two dimensions, which would be kind of like the collisions you might see on a pool table. Two-dimensional collisions are sometimes described as glancing or off-center collisions. There's effectively two types of two-dimensional collisions, inelastic and completely inelastic. Again, we're going to treat each individually, although the relationships all proceed from conservation of momentum. The off-centeredness of two-dimensional collisions will preclude them being elastic. What we'll find is that kinetic energy will be lost in the collision. Now, we know that we're going to proceed from conservation of momentum, which means P equals P prime. Once again, note the vector symbols. When we expand this to two dimensions, that's going to mean that conservation will apply in the x direction and also in the y direction. So it will follow that in two-dimensional collisions, Px will equal Px prime and Py will equal Py prime. To clarify the terms, Px refers to the x component of the system momentum before the collision. Px prime refers to the x component of the system momentum after the collision. Py is the y component of the system momentum before the collision, and Py prime is the y component of the system momentum after the collision. Note the repetitive nature of system momentum. We went over this in one dimension. We reiterate it in two dimensions, that when we say system momentum, it means all of the object's x direction momentum components added together. Okay, so there may be a lot of component manipulation to do in two-dimensional collisions. Px prime would indicate each of the objects in the system x component of its momentum after the collision added up. So we'll hit that pretty hard. Now, when we analyze two-dimensional collisions, we're going to set up a table of x and y components of the system momentum before and after the collision. There's a blank version here. It may look a little bit like a vector addition table. It is a little different. Notice that the x and y are the rows, and then the columns are going to refer to before and after the collision. So here's a sample of what a two-dimensional collision might look like. This looks like something you might see on a pool table. We're given object mass m1 here. We're given its initial velocity. We're also told that it's at 0 degrees mathematically, which means it's moving to the right. There's a stationary target ball. It's got a different mass, m2. We've got an off-center inelastic collision. After the collision, m1 is going to move off in this direction. We can see it's indicated here. So m1 is going to hit and bounce and go this way. We're given its final velocity and also the angle. 39.2 degrees is theta 1 prime. What we would, it says here, solve for the following. We would be effectively determining the velocity and direction of m2 after the collision. Now we're going to take our table, our blank table that we saw before, and we're going to adapt it to this particular situation. So here's what it would look like. Okay, we've got system momentum in the x direction before, system momentum in the y direction before, system momentum in the x direction after, system momentum and the y direction after. Now we want to look at each of these cells pretty carefully. In the before column, we have an x direction m1 v1. There's a question here: why do we not see m2 in either of these two columns? And your answer would be m2 is not moving, so it doesn't have any momentum before the collision. It's a stationary target, so it doesn't have any momentum to contribute to the system before the collision. When we look at the y direction before, this is 0 because the motion of m1 before the collision is purely in the x direction. Now, when we look after, it's a little more complicated. m1 v1 prime is m1's momentum after. It has an x component. That x component is to the right, so it's positive. m2 also has a momentum m2 v2 prime. It has an x component. There's my cosine theta 2 prime indicating the x component. This is also positive because m2 is moving to the right. When we look at the y direction after, m1 v1 prime sine theta 1 prime, it's moving up after the collision, so this is positive. m2 is moving down, so that's what makes this component negative. Now this is going to yield us two equations. Conservation of momentum applies in both directions, so before equals after in the x direction. That's going to give us this equation here, and before equals after in the y direction, which will give us this equation here. Now you can imagine turning the problem, changing the directions, setting it up so that you have a slightly different arrangement. The columns will look different, but the relationship remains. Px equals px prime, py equals py prime. Okay, now we'll take a look at completely inelastic collisions. We know that completely inelastic means that the objects stick together and move away from the collision as one object. Same principle applies. Px equals px prime, py equals py prime. After the collision, we'll have a single combined mass and a single velocity v prime. Now, here's what one of these might look like. This one's pretty complicated. We've got m1 moving with some initial velocity v1. It's given a mathematical direction beta 1. We've got m2 moving with some other velocity v2 with some other direction beta 2. The objects are going to collide here and stick together, and they're going to move away from the collision as a single mass, m1 plus m2. We want to take a look at the symbolic expressions for x and y direction, system momentum. Here's my table. Now, we want to consider each term carefully. We know that the beta terms are mathematical angles. Now, when we look at the x direction terms before the collision, we've got m1 v1. That's m1's momentum before. Cosine indicates the x component. We've got m2 v2. Cosine indicates the x component. Would you expect these to be both positive? You look at the image, they're both moving to the right initially, so we would expect them to both be positive. In the y direction, here's the y component of m1's momentum, here's the y component of m2's momentum. Looking at the image, we might conclude that this term should be negative because m1 is moving down initially. m2 is moving up initially. This term would be positive. Okay. Now, note something about the image after the collision. We don't know if m1 plus m2, if this combined mass is going to be moving to the right and up or to the right and down. We do know it's going to be moving to the right because both of these are moving to the right initially. But as far as up and down, we don't know, because with no data, we don't know which of these y components would have the greater magnitude. Whichever one does, that's the one that would win effectively. If M2's y component is bigger, it would be moving up afterwards. If M1's y component were bigger, it would be moving down afterwards. Okay? When we look at the after column, again, we have a combined mass, M1 plus M2. V prime cosine is my x component. V prime sine is my y component. Once again, before equals after. So this would equal this. This would equal this. Okay, one other thing. How could you use the x and y components of the system momentum to determine the system momentum in standard vector notation? These added up indicate the x direction momentum of the system. These indicate the y direction momentum of the system. We could use Pythagorean theorem and inverse tangent to figure out the system momentum in standard vector notation. Okay, also, if we know the system momentum before the collision, we also know the system momentum after the collision, which means before equals after. We could then use the system momentum to determine the velocity of the combined mass after the collision, because it's one mass moving with some single velocity v prime. Whatever direction that v prime has, that's going to be the direction of the system momentum, because we have a single combined mass. We'll see some examples of this in class. Of course, we could turn the image in a different direction. We could use realistic objects. Car and a truck, you'll see a problem like this. The truck and the car collide and move away from the collision as a single combined mass. You can imagine lots of possibilities here. Okay, so that'll do it for two-dimensional collisions. Next up is mechanical explosions, and we will see those shortly. Until next time, enjoy, and I'll see you again soon.